the 15th of March 1943, Saint-Nazaire, France. At 0430 hours in the pre-dawn darkness along the Atlantic coast, 22 RAF Lancaster bombers appeared over the massive German U-boat pens. Within minutes, over 42,000-pound blockbusters slammed into the reinforced concrete fortifications. When the smoke cleared, not a single bomb had penetrated. After-action reports from both sides recorded the same phenomenon. Conventional bombs shattered, shock waves dissipated, and the fortifications remained intact. The submarine war would continue unabated. The weapon was the Reich's newest defensive engineering, the Type VII U-boat pens. Introduced just 3 years earlier as a symbol of German engineering prowess and Atlantic dominance, designed to withstand the heaviest Allied bombs, these massive concrete fortifications featured roofs up to 23 feet thick, protecting the submarines that were bleeding Britain's maritime lifelines. Yet by 1944, these indestructible fortifications would be cracked open like eggs. How did the Allies defeat Germany's strongest fortifications, praised by military engineers for their design, when conventional bombs merely scratched their surface? The 17th of September 1941, London, England. On a drafting table at the Air Ministry lay blueprints labelled Earthquake Bomb, the brainchild of Barnes Wallis, a visionary engineer already known for his innovative Wellington bomber design. The Royal Air Force demanded a weapon capable of destroying targets conventional bombs couldn't touch, particularly the reinforced submarine pens threatening Britain's survival. Expectations were clear. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. Unprecedented size, penetrating power, and an entirely new concept in bomb design, not to explode on impact, but to penetrate deep before detonation, creating an earthquake effect that would destroy structures from below. But reality was already against them. Britain's conventional bombs in 1941, even the massive 4,000-pound blockbusters, were mere firecrackers against the German submarine bases. The U-boat threat was growing daily, with Allied shipping losses reaching catastrophic levels. The U-boat pens at Saint-Nazaire, Lorient, Brest, La Pallice, and Bordeaux had been constructed with lessons learned from World War I. Some featured concrete roofs over 23 feet thick, reinforced with steel rebar and designed specifically to withstand aerial bombardment. Each bomb that failed to penetrate these structures represented not just wasted ordnance, but lost ships, lost supplies, and ultimately, lost lives. Wallis understood the fundamental problem. Conventional bombs detonated on impact, dissipating their energy outward against the concrete surface. What was needed was something entirely different, a bomb that could reach the earth beneath the target before exploding. His calculations suggested that a sufficiently large bomb, dropped from high altitude to achieve maximum velocity, might penetrate not just the concrete but the ground beneath, creating a camouflet, an underground cavity that would cause the foundations to shift and crack. An archival fragment from Wallis's notes dated October 1941 states, "A missile must be developed capable of penetrating 20 feet of reinforced concrete before detonation. The weapon's success depends entirely on achieving sufficient impact velocity. The kinetic energy required to penetrate such barriers necessitates both exceptional mass and terminal velocity. Any compromise in either factor would render the weapon ineffective." Early designs called for a bomb weighing approximately 10 tons, a massive leap from anything the RAF had deployed before. The aerodynamics would need to be revolutionary, with a specially hardened nose capable of surviving impact with reinforced concrete without prematurely detonating. The bomb would need to be spin-stabilized to maintain accuracy, a challenge at such extreme weights. Production initially centered on concepts, calculations, and small-scale experiments. At Wallis's facility in Weybridge, tests were conducted using scaled models to validate the mathematics. Quality control had to be absolute. There could be no compromise in materials or precision. The cost per bomb was calculated at approximately £5,000, 5 times that of existing heavy bombs. The cause and effect relationship was already visible. Penetration of hardened targets required exceptional mass and velocity. Any disruption to the bomb's integrity, any flaw in its casing or ballistic properties would render it useless, and those disruptions were significant. The initial 10-ton earthquake bomb concept was deemed too heavy for any existing or projected aircraft. The RAF's heavy bomber, the Lancaster, could carry a maximum bomb load of approximately 14,000 pounds, well short of what Wallace initially calculated was necessary. Within 3 years, the same concept would be implemented at half the originally proposed weight, the 12,000-pound Tallboy. But questions remained whether this compromise would be sufficient against the most hardened targets. But in September of 1941, none of that was visible. The concept was sound. The mathematics were compelling. Britain believed it had conceptualized a bomb to crack open Germany's most hardened defenses. It had, for as long as the innovation held out against the realities of wartime constraints. December 1941, Royal Aircraft Establishment, Farnborough, England. Test range data showed side-by-side comparisons. Conventional 1,000-pound general-purpose bombs versus the proposed earthquake concept. Engineers recorded penetration depths, concrete fracturing patterns, and shockwave propagation. Results confirmed expectations. Conventional bombs created surface craters, but failed to seriously damage heavily reinforced structures. Penetrating bombs, even in small-scale tests, showed promising results against simulated bunkers. The mathematics were validated. A sufficiently large bomb with enough velocity could indeed reach beneath a target before detonating, creating an underground shockwave that undermined foundations in a way direct hits never could. Technical challenges emerged immediately. A bomb designed to penetrate concrete needed an exceptionally strong casing, particularly at the nose. Standard bomb steel would deform or shatter on impact with reinforced concrete. Special hardened steel alloys would be required, with precisely calculated tapering to maximize penetration while maintaining structural integrity. Stabilization presented another challenge. A bomb tumbling through the air would lose accuracy and penetrating power. Wallace designed the weapon to be spin-stabilized, rotating along its longitudinal axis at approximately 30 revolutions per second, achieved by angled fins that would catch the airstream during descent. But the most significant challenge was aircraft capacity. The Lancaster bomber, Britain's newest heavy bomber, could carry approximately 14,000 pounds of bombs, insufficient for Wallace's original 10-ton concept. Compromises would be necessary. After extensive calculations, Wallace reluctantly scaled his design down to 12,000 pounds, the absolute minimum he believed might still achieve the desired effect. A technical note from this period, translated from Wallace's own handwriting, observes, "Ballistic performance acceptable. Terminal velocity calculated at 2,650 feet per second. Penetration estimate, 16 to 20 feet of reinforced concrete, depending on angle of impact and concrete quality. This may prove sufficient against the secondary targets, but remains questionable for the primary U-boat pens." This was the first documented hint of the challenge that would define the bomb's development. Engineers flagged the danger of insufficient mass. Under ideal conditions, the reduced weight, Tallboy might penetrate the U-boat pens, but any deviation from perfect drop conditions would likely result in failure. The cause and effect chain was already forming. Reduction in bomb weight forced reliance on achieving maximum velocity. Maximum velocity required extreme drop altitudes and precise release conditions. Precise conditions were difficult to achieve in combat, especially under enemy fire. Even in late 1941, Wallace understood this, but wartime necessity overrode perfect solutions. The blueprint was sound, the physics were proven, but the compromise between what was theoretically needed and what was practically achievable would determine whether the hardened U-boat pens could ever be cracked. That imbalance between engineering ambition and operational reality would define the next 2 years of bombing campaigns as thousands of conventional bombs cratered the French coastline without stopping a single U-boat from sailing. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. February 1942, Coastal Command Headquarters, Liverpool, England. A situation map pinned to the wall showed a dramatic leap in shipping losses. Black pins representing sunken Allied vessels clustered along the convoy routes. Red triangles marking U-boat attacks formed patterns around the British Isles, extending increasingly into the Atlantic. In January alone, U-boats had sunk 62 ships, totaling 327,000 tons. In the first months after America's entry into the war, demand for effective anti-submarine measures soared. Allied naval headquarters planned increased convoy protection, expanded air patrols, and critically neutralization of the U-boat bases themselves. Existing arsenals of weapons could not meet this last requirement. The 5 major U-boat bases on the French Atlantic coast, Saint-Nazaire, Lorient, Brest, La Pallice, and Bordeaux, had been fortified beyond the capabilities of conventional bombs. Construction specifications obtained through intelligence channels revealed the scale of the challenge. The submarine pens featured layered concrete roofs up to 23 feet thick, reinforced with steel rebar arranged in complex patterns, specifically designed to absorb and distribute blast forces. Walls were similarly hardened, with some measuring over 11 feet thick. Between reinforced ceiling sections, drainage layers of sand and gravel absorbed shock and prevented water accumulation. An RAF intelligence assessment from March 1942 acknowledged the problem bluntly. Precision cannot be maintained under current bombing conditions. Standard ordnance lacks penetrating capabilities against these hardened structures. This was not a temporary setback. It was a fundamental mismatch between offensive capabilities and defensive engineering. The cause and effect relationship was straightforward. Increased concrete thickness exceeded bomb penetration capacity, while layered construction dissipated blast energy, and drainage layers between concrete sections prevented fracturing from transmitted shock. In operational terms, bombers were dropping their payloads into what amounted to enormous shock absorbers. RAF bombing raids against these targets throughout 1942 revealed the consequences. Squadrons of Wellington, Halifax, and Lancaster bombers delivered thousands of tons of explosives against the U-boat bases with minimal effect. Post-raid reconnaissance photographs showed cratered surroundings but intact pens. German repair crews could typically clear the debris and resume operations within hours. A bombing assessment dated August 1942 reported that despite delivering over 2,000 tons of bombs against the Lorient submarine base, no significant damage to primary pen structures observed. U-boat operations continue unimpeded. The human cost of these ineffective raids was measured in lost aircraft and crews. Each mission against the heavily defended U-boat bases cost an average of 5% of the attacking force aircraft and highly trained crews that Britain could ill afford to lose. Field reports began filtering back to London. Squadron leaders from Bomber Command reported that even direct hits with 4,000-pound blockbusters merely chipped the surfaces of the concrete fortifications. Bombs that struck the edges of the structures or near drainage systems sometimes caused localized damage, but nothing that impeded submarine operations. The Allied bombing forces faced a paradox. Raid intensity was increasing, but operational impact was minimal. More bombs were being dropped, fewer submarines were being damaged. The assembly line had become a symbol of Allied limitations. Factories could still produce bombs, load them onto aircraft, and deliver them to targets, but they could no longer guarantee that the bombs would achieve their intended purpose. The conventional bombing campaign was being built faster than ever and failing faster than ever. The Allied air forces were learning a bitter lesson. Engineering superiority required more than good planes and brave crews. It required weapons capable of defeating the target. August to October 1942, Barnes-Wallis returned to his calculations at Vickers Armstrong. Development of the smaller Tallboy had progressed, but production remained months away. Meanwhile, the U-boat war was reaching its zenith. German submarines sank 107 ships in August alone. With conventional bombing proving ineffective, alternate strategies emerged. One approach involved precision targeting of vulnerable points, the pen entrances, power facilities, and support infrastructure. If the fortifications themselves couldn't be destroyed, perhaps their functionality could be impaired. Special low-level raids were organized against lock gates, power stations, and submarine construction facilities. The most dramatic of these was the Saint-Nazaire raid of the 28th of March 1942, when British commandos rammed the HMS Campbelltown, loaded with delayed action explosives, into the lock gates of the submarine pen complex. The operation succeeded in destroying the massive dock gate, preventing larger U-boats from using the facility for repairs. But the submarine pens themselves remained operational. Another strategy involved mining the approaches to the bases and intensifying anti-submarine patrols in the Bay of Biscay, through which U-boats had to travel to reach their hunting grounds. This approach achieved some success, but the fundamental problem remained as long as the fortified pens existed. Submarines had safe havens from which to operate. By late 1942, Allied leadership recognized that cracking the U-boat pens would require a technological leap. Conventional high-explosive bombs, even the massive blockbusters, simply lacked the penetrating power to breach the reinforced concrete. The war against the U-boats was being lost in the Atlantic, and no amount of conventional bombing seemed capable of addressing the root cause. A technical impasse had been reached. The German fortifications represented the zenith of defensive engineering structures, specifically designed to withstand the most powerful bombs in the Allied arsenal. Something revolutionary was needed, and Barnes-Wallis's earthquake bomb concept, now evolved into the more practical Tallboy, appeared to be the only viable solution. In October 1942, the Air Ministry formally approved production of an initial batch of Tallboy bombs, with an expected delivery date of spring 1944. The decision acknowledged a sobering reality. For another year at least, the U-boat pens would remain effectively invulnerable to air attack. In that time, hundreds more Allied ships and thousands of sailors and passengers would be lost to submarines operating from these concrete sanctuaries. November to December 1942, Bristol Aeroplane Company, England. Engineering teams reviewed the finalized Tallboy designs. The weapon that emerged from Barnes-Wallis's calculations was unlike any bomb previously deployed. Weighing 12,000 pounds, it measured 21 feet in length with a diameter of 38 inches. Its distinctive shape, a long, slim body with a blunt, reinforced nose, resembled an enormous dart more than a conventional bomb. The casing was cast from a single piece of high-tensile steel, with walls nearly 5 inches thick. The nose was specially hardened through a molybdenum chrome steel alloy, heat-treated to achieve maximum hardness without becoming brittle. Internal cavities were filled with Torpex, a new explosive compound 50% more powerful than TNT. Perhaps most distinctive were the tail fins angled to induce rotation during descent, stabilizing the bomb's trajectory and increasing accuracy. This spin stabilization was crucial for ensuring the bomb struck at the optimal angle for penetration. Manufacturing challenges were immense. The specialized steel required precise alloying and careful heat treatment. Each bomb casing needed to be cast as a single piece to avoid weak points, necessitating massive foundry equipment. The nose section required additional hardening treatments. Explosive filling had to be perfectly centered to maintain ballistic properties. A manufacturing specification from December 1942 outlined the exacting requirements. Casing hardness must achieve Brinell 240 to 280 throughout. Surface finish tolerance plus or minus 0.05 inches. Weight distribution must maintain center of gravity within 0.25 inches of calculated position. Any deviation compromises ballistic performance and may result in failure to achieve penetration. January 1943, Liverpool, England. Admiral Karl Dönitz's wolves were hunting in packs. Situation rooms tracking convoy movements displayed the grim reality. 37 Allied ships sunk in the first 2 weeks of the year alone. This wasn't just a naval war, it was an existential threat. Without supplies from America, Britain faced starvation. The shipments, the planned liberation of Europe, would remain a distant dream. In a basement war room beneath the Admiralty building, intelligence officers pinned photographs to cork boards. The images showed concrete fortresses along the French coast: Saint-Nazaire, Lorient, Brest, La Pallice, Bordeaux, U-boat pens that conventional bombing couldn't touch. Submarines entered these shelters, replenished, repaired, and returned to the Atlantic killing grounds with near impunity. The human cost was staggering. Each ship lost meant dozens, sometimes hundreds of sailors and merchant seamen dead. Precious cargo food, medicine, ammunition now rested on the Atlantic seabed. The convoys continued sailing because they had to, but morale was deteriorating as crews watched helplessly while torpedoes claimed ship after ship. A weathered Royal Navy captain with salt and pepper beard addressed the room. "Gentlemen, this war will be won or lost on merchant shipping. As long as those concrete pens stand, our losses will continue to mount." The problem wasn't merely tactical, it was a fundamental mismatch between offensive and defensive technology. Meanwhile, at the Ministry of Aircraft Production, Barnes-Wallis's team raced against time. The Tallboy design had moved from drawings to prototype, but production hurdles loomed large. Each bomb required precise casting of high-tensile steel, specialized machining, and exacting quality control. The first test models wouldn't be ready until mid-1943, and full production remained distant. Operational analysis painted a stark picture. In the interim, conventional bombing would continue against the submarine pens, consuming aircraft, ordnance, and crews, while achieving minimal results. Bomber Command estimated that to maintain pressure on the U-boat bases, approximately 200 sorties per week would be required. At typical loss rates of 5%, that meant 10 aircraft and 70 airmen lost weekly to a campaign that wasn't achieving its primary objective. Behind closed doors, Air Chief Marshal Sir Arthur Harris expressed frustration. "We're expending blood and treasure against targets we cannot meaningfully damage. Each raid that fails to penetrate those concrete monstrosities strengthens German confidence." The strategic dilemma was painful: continue an ineffective bombing campaign at great cost, or abandon the effort and concede the U-boat sanctuaries. Amid this atmosphere of urgency, Wallis pushed his teams to overcome technical obstacles. The specialized steel alloys required precise temperature control during casting and heat treatment. Any deviation in carbon content or cooling rates would compromise the bomb's penetrating power. Machinists worked to tolerances measured in thousandths of an inch, knowing that ballistic performance depended on perfect aerodynamics. By early spring 1943, the first prototype Tallboy casings emerged from the foundry, massive steel shells weighing over 5 tons even before being filled with explosives. Test engineers subjected these casings to simulated impact stresses, confirming the nose section could withstand collision with reinforced concrete without shattering. But the clock was ticking. U-boats were sinking Allied shipping faster than replacement vessels could be built. In March 1943 alone, 108 ships were lost, totaling over 600,000 tons. Without a solution to the U-boat pen problem, the Atlantic lifeline might snap. April to June 1943, Ashley Walk Bombing Range, New Forest, England. Test engineers constructed concrete bunkers designed to mimic sections of the U-boat pens. Some featured roofs up to 15 feet thick, though still short of the 23-foot monsters protecting the actual submarine shelters. Against these targets, conventional bombs were dropped for comparison purposes, creating surface craters, but leaving the structures intact. Parallel to Tallboy's development, another approach was gaining traction: overwhelming force. If individual bombs lacked penetrating power, perhaps hundreds or thousands of bombs dropped in the same area might achieve what single weapons could not. This concept led to massive raids involving hundreds of aircraft, concentrating their payloads on single targets. The results were disappointing. On the 17th of May 1943, 197 bombers attacked the submarine pens at Lorient, dropping over 600 tons of bombs. Reconnaissance photographs taken the following day showed extensive damage to surrounding buildings, streets, and harbour facilities, but the reinforced pens remained operational. Submarines inside continued maintenance and preparations for their next patrols. A technical assessment from RAF Bomber Command, dated June 1943, concluded, "Concentration of conventional ordnance has proven ineffective against primary targets. Damage to surrounding infrastructure temporarily impedes operations, but does not prevent U-boat deployment. Only a purpose-built penetrating weapon offers reasonable probability of success." The cause and effect was becoming clearer. Reinforced concrete of sufficient thickness distributed blast energy so effectively that even massive conventional bombing created only surface damage. The physics were unyielding without penetration before detonation. The explosive force dissipated against the surface rather than compromising the structure. By mid-1943, Allied leadership faced difficult choices. The resources devoted to bombing the U-boat bases were yielding minimal strategic returns. Yet, abandoning the effort would leave the submarine fleet with secure havens. The war in the Atlantic had reached a technological impasse, with German defensive engineering temporarily outpacing Allied offensive capabilities. Admiral Sir Max Houghton, Commander-in-Chief of Western Approaches Command, summarized the situation in a memorandum. "Until these fortifications can be neutralized, our anti-submarine efforts must focus on convoy protection and Bay of Biscay patrols. We must kill the wolves at sea, since we cannot yet destroy their dens." This strategic pivot had immediate effects. Resources previously allocated to bombing the submarine pens were redirected. Long-range aircraft equipped with improved radar began intensive patrols over the Bay of Biscay, hunting U-boats as they travelled to and from their bases. Convoy escort groups were strengthened with additional destroyers and corvettes. Intelligence efforts to track submarine movements intensified. The shift in tactics began showing results. By summer 1943, U-boat losses were mounting while their effectiveness was declining. In May 1943, Dönitz temporarily withdrew his submarines from the North Atlantic convoy routes after suffering devastating losses. The tide of the U-boat war was turning not because the concrete fortresses had been cracked, but because the submarines themselves were increasingly vulnerable during transit. Yet the fundamental problem remained. As long as the U-boat pens stood, Germany maintained the capability to launch submarine operations. If Allied pressure in the Bay of Biscay decreased due to weather, shifting priorities, or tactical adjustments, the U-boat threat could resurge. The fortifications had to be neutralized. July to September 1943, Vickers Armstrong Works, England. The first production Tallboys took shape. Each bomb required approximately 180 man-hours of skilled labour to produce. The steel casings were cast in one piece, then machined to exacting tolerances. The nose sections underwent special hardening treatments. Explosives were carefully loaded to ensure perfect weight distribution. Tail fins were precisely angled to create the stabilizing spin during descent. Production capacity remained limited. Initially, only 10 Tallboys could be manufactured per week, a tiny number compared to the thousands of conventional bombs flowing from factories. Each Tallboy represented a substantial investment in materials, labour, and specialized equipment. The first, the operational batch, was prioritized for No. 617 Squadron RAF, the famous dam busters, who had successfully breached the Möhne and Eder dams in May 1943 using Barnes-Wallis's earlier innovation, the bouncing bomb. This elite squadron, commanded by Wing Commander Leonard Cheshire, had demonstrated the precision bombing skills necessary to effectively deploy the new weapon. Training for Tallboy operations began in early autumn 1943. The specialized nature of the weapon required new delivery techniques. The bomb needed to be dropped from at least 18,000 feet to achieve terminal velocity sufficient for penetration. This high-altitude approach made accuracy challenging. To compensate, 617 Squadron pioneered new precision bombing methods, including the use of target-marking aircraft and specialized bomb sites. The physics of the weapon demanded perfection. A tallboy striking reinforced concrete at the wrong angle would skid rather than penetrate. The ideal impact angle was nearly vertical, between 70 and 90 degrees. Achieving this required careful calculation of release point, accounting for wind drift, aircraft speed, and the bomb's ballistic properties. Engineering briefings emphasized the cause and effect relationship. Precise delivery conditions would enable maximum penetration. Penetration would place the explosion underground. Underground detonation would create a camouflet cavity. The camouflet would undermine foundations, and undermined foundations would compromise structural integrity. The entire chain depended on the first link accurate delivery from high altitude. By October 1943, the weapon system was deemed ready for operational use, though quantities remained severely limited. Target selection became critical with so few tallboys available. Each mission had to offer maximum strategic return on investment. While tallboy development progressed, conventional bombing of the submarine pens continued, though at reduced intensity. The results remained predictably disappointing. A raid on the Saint-Nazaire facility on the 9th of October 1943, involving 60 bombers, created extensive damage to surrounding areas, but left the protective concrete bunkers essentially intact, post-raid assessment noted. Primary structures undamaged. U-boat operations temporarily slowed due to access difficulties, but submarines within pens remain operational. The pattern was depressingly consistent. Conventional bombs, even 4,000-pound blockbusters, lacked the penetrating power to breach the reinforced concrete. The Allies could damage supporting infrastructure, crater access roads, and destroy adjacent facilities, but the submarines themselves remained protected within their concrete shelters. As 1943 drew to a close, the strategic picture had evolved. The Battle of the Atlantic had turned in the Allies' favor, but not because the U-boat pens had been neutralized. Improved convoy tactics, long-range air patrols, better radar, and signals intelligence had combined to make the submarines increasingly vulnerable at sea. U-boat losses were mounting, with 237 submarines sunk in 1943 alone, nearly half the operational fleet. Yet the concrete fortresses along the French coast remained symbols of German resilience and engineering prowess. Their continued existence represented a potential threat if Allied anti-submarine efforts slackened, or if new U-boat technologies emerged. The submarine campaign could revive. The fortifications had to be cracked. November 1943 to February 1944, RAF Woodhall Spa, Lincolnshire. No. 617. Squadron prepared for the first operational use of tallboy. The specialized nature of the weapon required extensive training. Precision release procedures, high-altitude flying techniques, and new bombing approaches were practiced relentlessly. Squadron pilots and navigators studied the physics behind the weapon. They understood that delivering a tallboy wasn't merely about dropping ordnance on target. It was about creating specific impact conditions that would maximize penetration. The release point had to be calculated with unprecedented accuracy, accounting for altitude, airspeed, wind, and the bomb's ballistic properties. Ground crews received specialized training in handling the massive weapons. Each tallboy weighed 12,000 pounds, 6 tons of precisely engineered destruction. Loading them into Lancaster bombers required careful procedure to avoid damage to either the bomb or the aircraft. Special hoisting equipment was developed specifically for handling these enormous weapons. Meanwhile, target planners assessed which objectives would provide the best demonstration of tallboys' capabilities. The U-boat pens remained primary targets, but their 23-foot reinforced concrete roofs presented extreme challenges. Even tallboy, for all its innovation, might struggle to penetrate such massive protection. Initial operations might need to target less heavily fortified structures to prove the concept before tackling the submarine bases. Intelligence officers compiled detailed information on the construction of potential targets. Architectural plans, concrete specifications, reinforcement patterns, and foundation details were analyzed to determine vulnerability to Tallboys' earthquake effect. The weapon's unique capability, penetrating the earth beside a structure before detonating, could potentially undermine foundations without requiring direct penetration of the heaviest reinforcement. By early 1944, the strategic context was evolving rapidly. Planning for Operation Overlord, the Allied invasion of Normandy, was advancing. The U-boat threat, while diminished, remained significant. German submarine bases along the French coast posed a potential threat to invasion shipping. Neutralizing these bases took on new urgency. In February 1944, final preparations for Tallboys' operational debut were underway. The first batch of production weapons had been delivered to RAF Woodhall Spa. Each bomb was handled with extraordinary care. These weren't merely explosives, they represented the culmination of years of research, engineering, and production effort. A technical briefing for 617 squadron crews highlighted the weapon's unique properties. Terminal velocity approximately 3,600 feet per second. Penetration capability estimated at 16 to 20 feet of reinforced concrete under optimal conditions. Underground detonation creates earthquake effect with damage radius extending beyond the immediate impact point. Precision delivery essential to mission success. The 14th of March 1944, Saumur, Loire Valley, France. At 21:45 hours, 12 Lancaster bombers of 617 Squadron approached their target, a railway tunnel used by German forces to move supplies toward the Atlantic coast. This was not a U-boat pen, but the mission would serve as the first operational test of Tallboys' capabilities against hardened structures. The target was selected specifically to demonstrate Tallboys' earth-penetrating effect. Rather than attacking the tunnel entrances directly, the bombing plan called for weapons to be dropped into the hillside above the tunnel. If successful, penetration and underground detonation would collapse the tunnel without requiring direct hits on the reinforced entrances. Weather conditions were optimal, clear visibility, light winds. From 18,000 feet, squadron leader Leonard Cheshire directed the attack, using marker bombs to indicate the precise aiming point above the tunnel. Following aircraft released their Tallboys with meticulous attention to timing and position, the results exceeded expectations. Of the 8 Tallboys dropped, 6 hit within the target area. Their penetration into the hillside before detonation created precisely the earthquake effect Wallace had predicted. The underground shock waves propagated through the limestone, causing the tunnel to collapse along a 150-yard section. Reconnaissance photographs taken the following day confirmed the tunnel was completely blocked, severing a critical supply route. Technical assessment of the mission noted camouflage effect conclusively demonstrated. Underground detonation more effective against this target type than surface explosion would have been. Concept validated under operational conditions. This first success, while not against a U-boat pen, demonstrated Tallboys' fundamental advantage, the ability to deliver destructive force below the surface, where conventional bombs could not reach. The implications were clear. Structures that had proven invulnerable to surface blasts might now be vulnerable to attack from below. Following this initial validation, target selection shifted toward more heavily fortified objectives. Planning began for operations against V-weapon sites, heavily reinforced command bunkers, and ultimately the submarine pens that had defied conventional bombing for years. April to May 1944, the pace of preparation accelerated. Production of Tallboys increased, though the weapons remained scarce compared to conventional ordnance. No, 617 Squadron continued to refine their delivery techniques, achieving greater accuracy from high altitude. Intelligence gathering focused on identifying the most vulnerable points of the U-boat pen structures, where foundations might be susceptible to underground shock, where concrete thickness varied, or where adjoining structures created potential weak points. In parallel, an even larger weapon based on similar principles was nearing completion, the 22,000-pound Grand Slam. This behemoth, essentially a scaled-up tallboy, promised even greater penetration and destructive power against the most hardened targets. But its enormous size limited the aircraft capable of carrying it to specially modified Lancasters with engines running at higher power settings. On May 8–9, 1944, 617 Squadron conducted operations against railway targets in France, using tallboys to collapse tunnels and viaducts that couldn't be destroyed by conventional bombing. Again, the weapon's unique capabilities were demonstrated penetration followed by underground detonation produced effects impossible to achieve with surface explosions. With D-Day approaching, Allied air planners prioritized transportation targets to isolate the invasion beaches from German reinforcement. The U-boat pens, while still strategic objectives, temporarily took lower priority. Yet planning continued for eventually bringing Tallboys' unique capabilities to bear against these most challenging targets. June 1944, Allied Headquarters, England. The greatest armada in history had crossed the Channel. D-Day had succeeded, but the push inland was slow and costly. Planners studied maps marked with the submarine bases still threatening Allied shipping. A naval commander jabbed his finger at Saint-Nazaire. Those U-boats are still sailing. Every supply ship they sink means less ammunition, less fuel, fewer reinforcements for our boys in Normandy. The submarine threat had diminished significantly since 1943, but it hadn't disappeared. From their concrete fortresses, U-boats continued to sortie into the Atlantic, now equipped with snorkels that allowed them to remain submerged longer, making them harder to detect. The invasion of Europe had changed the strategic calculus. Every ton of supplies lost to submarine attack directly impacted the ground campaign. Air Marshal Sir Arthur Harris reviewed the latest intelligence on the U-boat pens. "We've hit them with everything in our conventional arsenal. The results speak for themselves: cratered approaches, damaged infrastructure, but those damned concrete roofs remain intact." The time had come to deploy the specialized weapons designed specifically for this challenge. On June 8–9, 1944, just days after the Normandy landings, the first tallboy attack against a U-boat facility was authorized. The target, Saumur Rail Tunnel, not a submarine pen, but a critical supply route, supporting German forces in western France. While not directly attacking the submarine bases, this mission would further validate Tallboys' capabilities against hardened structures before committing the scarce weapons against the most challenging targets. The mission proved decisively successful. Tallboys penetrated the earth above the tunnel, creating underground explosions that collapsed the structure without requiring direct hits on the reinforced entrances. Post-strike analysis confirmed what Barnes-Wallis had predicted years earlier: underground detonation could accomplish what surface explosions could not. With this validation, planning accelerated for operations against the primary targets, the submarine pens themselves. Intelligence officers pored over reconnaissance photographs, construction blueprints, and reports from the French resistance. They identified potential weak points, transitions between different concrete pours, adjoining structures with different foundation depths, underground service tunnels, and areas where the full thickness of concrete might not extend. The challenge remained daunting. The main roofs of the U-boat pens featured concrete up to 23 feet thick, potentially beyond even Tallboys' penetration capabilities. But the structures weren't uniformly protected. Side walls, connection points, and some sections of roof had less reinforcement. Strategic targeting of these vulnerabilities might achieve what years of conventional bombing had failed to accomplish. July 1944, RAF Woodhall Spa. Wing Commander James Tate briefed the crews of 617 Squadron. "Gentlemen, we've been tasked with cracking the uncrackable. For 3 years, these concrete monsters have shrugged off everything we've thrown at them. Tomorrow, we change that equation." Maps and architectural diagrams covered the walls. Intelligence officers pointed out specific aiming points. Primary targets are these junction areas where the main pens connect to the outer structures. Secondary targets are the side walls, where concrete thickness is reduced. Precision is critical. A miss by more than 50 feet will likely result in minimal damage. The physics of the attack plan was explained in detail. Tallboys would be released from minimum 18,000 feet. Terminal velocity would approach 3,600 feet per second. At optimal impact angles, penetration of 15 to 20 feet of reinforced concrete might be achieved. Even if full penetration of the main roof wasn't possible, near misses causing underground detonation could potentially undermine foundations or create structural stress through soil displacement. On the 6th of July 1944, the first direct tallboy attack against a U-boat pen was launched. The target, Mimoyex, technically not a submarine base, but a V-weapon site with concrete protection comparable to the U-boat pens. This would serve as the final validation before committing the scarce weapons against the submarine fortresses. 16 Lancaster bombers of 617 Squadron, each carrying a single 12,000-pound tallboy, approached the target at 18,000 feet. Weather conditions were perfect, clear visibility, light winds. Target markers accurately identified the aiming points. The bombers released their weapons with meticulous precision. The results were beyond expectations. Several tallboys achieved direct penetration of the reinforced concrete, while others detonated underground, creating the earthquake effect Wallace had envisioned. Post-strike reconnaissance revealed catastrophic damage to the facility. Concrete that had defied conventional bombing for months had been breached. Technical assessment was unequivocal. Penetration of reinforced concrete verified. Both direct hits and near misses produced significant structural damage. Camouflage effect created foundation displacement extending beyond immediate impact points. The weapon had proven its capability against exactly the type of hardened structure it was designed to defeat. With this final validation, the path was clear for operations against the primary targets. On the 25th of July 1944, the order was given for the first tallboy strike against the submarine pens at Brest. Intelligence suggested this facility had sections where concrete reinforcement was less comprehensive than at Saint-Nazaire or Lorient, making it an ideal initial target. 18 Lancasters, led by squadron leader Calder, approached Brest from 19,000 feet. Anti-aircraft fire was intense. German defenders understood the threat these specialized bombers presented. Despite the defensive barrage, the squadron maintained precise formation, releasing their tallboys on the squadron leader's mark. Direct observation of impacts was difficult through the smoke and dust, but crews reported multiple precise hits. A gunner in one Lancaster described what he witnessed. "I saw one tallboy strike the edge of a pen roof. There was a brief flash, then nothing the bomb had penetrated before detonating. Seconds later, a massive heave in the structure, like the concrete was breathing, then collapse along one entire section. Reconnaissance aircraft dispatched the following day brought back phenomenal images. For the first time since their construction, the submarine pens at Brest showed critical damage. One pen had partially collapsed, with massive concrete sections displaced. Another showed severe cracking along structural seams. A third had a penetration hole approximately 15 feet in diameter, indicating a direct hit had punched through the protective roof. German repair crews scrambled to assess and mitigate the damage. Unlike previous raids, where surface cratering could be cleared in hours, the structural damage caused by tallboys required major engineering intervention. Several submarines trapped inside damaged pens were unable to deploy, effectively neutralized without being directly hit. Analysis of the strike results confirmed the weapon's effectiveness. Tallboys demonstrated three distinct damage mechanisms: direct penetration followed by internal detonation, near-miss underground explosion creating foundation displacement, and edge strikes exploiting structural transition points. All three mechanisms produced damage impossible to achieve with conventional bombs. The psychological impact was equally significant. German naval personnel, who had grown accustomed to the security of their concrete shelters, suddenly found themselves vulnerable. A captured German naval officer later confessed, After the Tallboy raids, morale collapsed. Men who had felt invulnerable now hesitated to enter the pens. Every unusual sound was interpreted as structural failure. August 1944 brought a strategic shift. Allied advances across France threatened to overrun the Atlantic submarine bases. German forces prepared for potential evacuation, moving some submarines to Norwegian facilities beyond the reach of Tallboy-equipped aircraft. Despite this shifting front, Bomber Command authorized continued strikes against the concrete fortresses. The rationale was twofold: prevent submarines from conducting last-minute operations against Allied shipping, and deny the Germans the opportunity to destroy the facilities themselves, potentially leaving them intact for Allied use. On the 6th of August 1944, the submarine pens at Lorient, among the most heavily reinforced of all the Atlantic bases, became the target. 20 Lancasters of 617 Squadron, joined by aircraft from 9 Squadron, carried Tallboys to the target. Weather conditions were less than ideal, with cloud cover complicating accurate delivery. Despite these challenges, the raid achieved significant success. 3 Tallboys struck the main pen complex directly. 2 others hit within 50 feet of the primary structure, creating underground detonations. Post-strike reconnaissance showed major structural damage: concrete roof sections displaced, massive cracking along load-bearing walls, and one pen entrance completely blocked by collapsed material. A technical assessment from RAF Bomber Command noted, Tallboy performance against the Lorient facility exceeded expectations. Penetration achieved through concrete previously considered impervious to aerial bombing. Earthquake effect clearly demonstrated, with damage extending beyond immediate impact points. The operational impact was immediate. U-boat departures from Lorient ceased completely. Submarines already inside the damaged pens remained trapped, unable to exit through blocked passageways, or unwilling to risk passage through structurally compromised sections that might collapse at any moment. September 1944. As Allied ground forces approached the Atlantic coast, German Naval Command faced a dilemma. The concrete fortresses they had built to withstand bombardment from the air were now threatened from the land. Orders were issued to prepare demolition charges. If the bases couldn't be held, they would be destroyed to prevent Allied use. But time was running out. On September 18 to 19, 1944, the most ambitious Tallboy operation yet was mounted against the submarine pens at Saint-Nazaire, the largest and most heavily protected of all the Atlantic bases. 27 Lancasters, each carrying a Tallboy, approached the target. This concentration of these specialized weapons represented a significant portion of the entire production run to that date. The raid was meticulously planned. Target markers identified precisely the junctions between different construction phases of the complex, where concrete bonding might be weaker. Other aiming points focused on side walls and access points, where reinforcement was less comprehensive than the main roofs. Results were devastating. Multiple direct hits penetrated sections of the protective structure. Underground detonations from near misses created the earthquake effect in spectacular fashion. Entire concrete platforms shifted, massive cracks appeared in walls previously impervious to bombing, and one entire section of roof collapsed into the pen below, crushing a Type VII U-boat undergoing maintenance. Reconnaissance photographs revealed the extent of the damage. For the first time, the massive Saint-Nazaire complex showed critical structural failure. German repair attempts proved futile. The damage was too extensive, affecting load-bearing elements throughout the complex. Submarines within the damaged sections were effectively entombed, unable to deploy. A captured German naval engineer later described the impact. "We had absolute confidence in our concrete. After all, it had withstood thousands of bombs." Then came these new weapons. The physics was entirely different. Instead of absorbing impact on the surface, our structures were being attacked from within or below. Against this, we had no defense. By October 1944, the strategic situation had evolved dramatically. Allied forces had liberated much of the French coast. German forces still held several isolated ports, including Saint-Nazaire, but their operational capacity was severely limited. Submarines attempting to operate from the damaged facilities faced increased risk not from Allied bombs, but from the structural instability of their own protective bunkers. On the 14th of October 1944, the most spectacular demonstration of Tallboys' capabilities occurred at Sorp Dam in Germany. While not a submarine pen, this mission illustrated the weapon's unique destructive potential against massive reinforced structures. A single Tallboy, dropped with exceptional precision, penetrated deep into the dam's structure before detonating. The resulting damage was catastrophic, massive internal fracturing that traditional bombs could never have achieved. This success reinforced the decision to continue operations against the remaining submarine facilities. On the 2nd of November 1944, Bergen in Norway, where many U-boats had relocated following the damage to French bases, became a target. The submarine pens there, while formidable, lacked the extreme reinforcement of the Atlantic bases. 18 Lancasters delivered Tallboys with devastating effect. Multiple penetrations were achieved, with internal detonations causing catastrophic damage. One eyewitness account described the scene. It was as if the earth itself had rejected the concrete. The structure didn't just crack, it heaved upward before collapsing in on itself. Massive reinforced sections weighing hundreds of tons were tossed aside like toys. By December 1944, the operational picture was clear. The submarine pens, once considered impregnable, had been decisively compromised. Those still in German hands were either severely damaged or under constant threat of attack with weapons they could not withstand. The psychological impact was equally significant. The myth of concrete invulnerability had been shattered. German Naval Command acknowledged the reality in a December 1944 assessment. The enemy has developed a weapon specifically engineered to defeat our protective structures. Continued operations from fixed facilities cannot be guaranteed. Relocation of remaining assets to dispersed facilities is recommended. The new year brought the final phase of Tallboy operations against the submarine threat. The 12th of January 1945 witnessed the most concentrated attack yet. 32 Tallboys dropped on the remaining operational facilities at Bergen. This overwhelming force achieved what years of conventional bombing had failed to accomplish: the systematic destruction of Germany's submarine infrastructure. Post-strike assessment was unequivocal. Target effectively neutralized. Multiple penetrations observed. Structural failure extends throughout the complex. Repair considered impossible under current conditions. Submarine operations from this facility no longer viable. February 1945, RAF Scampton, England. Barnes Wallis stood before a group of engineers and aircrews. Behind him, photographs showed the shattered remains of concrete structures once thought impregnable. "Gentlemen," he began, "3 years ago we faced a problem that conventional approaches could not solve. The physics of the challenge required us to think differently, not just about making bigger bombs, but about fundamentally changing how they delivered their energy." He pointed to a cutaway diagram of a Tallboy. "This is not merely a weapon, it is the physical embodiment of a concept that penetration before detonation creates effects impossible to achieve with surface explosions. That earth itself, properly harnessed, becomes part of the destructive mechanism." The evolution of Tallboy had reached its culmination with the even larger Grand Slam, a 22,000-pound monster carrying over 9,000 pounds of Torpex explosive. This behemoth, essentially a scaled-up Tallboy, promised even greater penetration against the most hardened targets. First used operationally in March 1945, Grand Slam demonstrated devastating effectiveness against structures that even Tallboy struggled to defeat. March to May 1945. The final offensive against Germany's remaining submarine infrastructure combined Tallboys and Grand Slams in devastating harmony. Facilities in Hamburg, Kiel, and remaining Norwegian bases were systematically reduced to rubble. The concrete fortresses, designed to protect Germany's submarine fleet through years of war, lay broken and useless. The technical assessment was definitive. Penetration weapons have fundamentally altered the equation between offensive and defensive technology. No purely passive defense, regardless of material thickness, can withstand attacks that bypass surface protection and attack from within or below. Tallboys' journey from concept to operational weapon encompassed the entire arc of the war against the U-boat. From the desperate days of 1941, when submarines threatened Britain's survival, to the final offensive of 1945, when the once mighty U-boat fleet had been reduced to ineffectiveness. Throughout that journey, the weapon represented the triumph of innovative thinking over seemingly insurmountable obstacles. May 1945, Berlin. The Third Reich collapsed. Among the documents captured by Allied forces were German engineering assessments of the damage inflicted by Tallboy and Grand Slam. Technical drawings showed proposed countermeasures, even thicker concrete, layered air gaps, new foundation designs, all attempting to counter the earthquake effect. None had progressed beyond the planning stage. The war had ended before these defensive measures could be implemented. A German engineering report dated March 1945 acknowledged the fundamental problem. Current protective structures were designed to resist bombs detonating on or near the surface. The enemy has developed weapons that change this paradigm entirely. Protection against underground shock waves requires completely different approaches than protection against direct impact or blast pressure. The story of Tallboy represents more than just a specialized weapons development. It embodies the principle that seemingly insurmountable obstacles often require fundamentally new approaches, rather than incremental improvements to existing methods. When conventional bombing proved ineffective against reinforced concrete, the solution wasn't simply bigger conventional bombs, it was a complete rethinking of how explosive energy could be delivered. This insight has relevance far beyond military technology. In any field, when traditional approaches reach their limits, breakthrough innovations often come from questioning fundamental assumptions rather than refining existing methods. The path from problem to solution isn't always linear. It sometimes requires stepping back to reconsider the entire framework. Barnes Wallis himself summarized this philosophy. Engineering is not merely about building things stronger or bigger, it's about understanding the underlying principles and applying them in ways others haven't considered. Sometimes the solution isn't more power, it's power applied more intelligently. The concrete fortresses of the Atlantic coast stand today as silent monuments, many still too solid to demolish economically, despite 75 years of exposure to the elements. Their scarred surfaces and collapsed sections bear witness to the contest between defensive engineering and offensive innovation that played out during those desperate years. In the end, no fortress proved truly impregnable, no defense absolutely secure. The massive concrete bunkers, designed to withstand years of bombing, ultimately succumbed to weapons specifically engineered to defeat them. The lesson is timeless. Adaptation and innovation will eventually overcome even the most formidable obstacles. The legacy of Tallboy extends beyond its immediate military impact. Its development process, identifying the fundamental physics of the problem, challenging conventional approaches, and meticulously engineering a precise solution, exemplifies problem-solving at its most effective. When facing our own seemingly insurmountable challenges, we would do well to remember the lesson of those cracked concrete pens. Sometimes the solution isn't hitting harder, it's hitting smarter. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.